I'm excited to tell you about the latest progress we made with the DGX Quantum product that we are building in the company. To set the stage, let me tell you a bit more about what DGX Quantum is. DGX Quantum is an exclusive partnership between NVIDIA and Quantum Machines to build the full quantum control computing stack, enabling you to connect at ultra-low latency classical resources given by an NVIDIA Grace Hopper chip connected to an OPX 1000, fully powered by our classical hybrid processing unit. In this demo, I will show you how we can leverage this super nice architecture to perform quantum gate calibration. So, to set the stage a bit more, what are we talking about when we are talking about gate calibration? In our scenario where we aim towards fault tolerance, we need to ensure that in the long term, all our physical error rates will be as low as possible. To do that, we need to make sure that we can efficiently suppress noise at the lowest level possible. When we start with usual physical models for our quantum gates, this is usually a very good start. But as devices scale up, we anticipate that you will definitely need a closed-loop optimization mechanism to complete the description of your quantum gates, to make sure that you are as accurate as possible when executing your pulses on your qubits. So this is why we chose to adopt a technique that was introduced a few years ago for quantum control, namely reinforcement learning. And you will see that the usual bottleneck that we face when trying to do closed-loop optimization in a quantum control scenario is that we constantly have to evaluate some parameters on the quantum computer and eventually stream them back to the classical computer, and doing so iteratively. The main issue that people encounter is what we call the compilation overhead. Each time you have to try out a new set of parameters, you usually have to involve a recompilation step where the quantum circuit you wanted to execute will now be slightly different based on your parameters. However, when we're doing a gate calibration task specifically, we already know in advance which set of parameters we're going to be interested in tuning. And the circuit structure is going to mostly remain the same. So we want to take advantage of this to lower as much as possible the compilation overhead. But on top of this compilation stuff, we also want to address the latency issue induced by the communication pipeline. By communication, I mean how much time does it take you to load information from the classical computer, the pulse parameters, to the quantum computer. And same thing with the measurement outcomes. We want to stream this data as fast as possible. And this is exactly what DGX Quantum is about, enabling you to stream your process as fast as you can. With a below 4 microsecond latency of round trip, you can make sure that this calibration is going to run in a nutshell. Let me now show you the setup in which we are getting this reinforcement learning going on. So in this particular scenario, we have typically two main entities. One is the agent, and the other is the environment. The agent mission, represented by this classical computer and this neural network, is in charge of one mission: finding the right set of parameters, what we also call actions in the reinforcement learning community, to steer our desired environment in a specific target. In this particular case, the environment is our quantum computer, and the target will either be our target state or a target gate that we're trying to come up with. In this demo, for the sake of simplicity, we will try to prepare a bell state. So the objective is to make sure that we can choose the set of actions which will prepare a unitary, effectively creating this bell state. So let me show you now. Just before we switch to the actual demo, let me just give you one additional detail, which is about the feedback. So we saw what the agent is sending to the quantum computer. Let's see what the quantum computer sends back to the agent. In this feedback loop, we want to rely solely on measurement outcomes. This ensures that we can avoid any model bias that would typically mask some of the noise complexities that we might experience in hardware. So the more we're going to sample from the experiment, the more we're going to be knowledgeable about what's actually going on. And the agent, in its model-free fashion, will try to fight its noise at its best by finding the right action compensating this noise. So the reward in this case becomes some kind of signal which tells you how close you are to your target state. So you can pretty much guess that this is going to be an instance metric based on the fidelity, for instance. And in the bell state specifically, computing a fidelity estimator is actually very easy. Why is that? The bell state, among many other GHZ states, of course, is a stabilizer state. Namely, we only need a very few Pauli observables to describe the state. In this case, 3 observables, XX, YY, and ZZ. In essence, what we'll need to do is compute expectation values for one typical action of those 3 expectation values, sum them up in the formula that you see on the screen, and eventually give this back to the agent. Okay, one last thing about the action space. So what are the parameters that our agent is trying to optimize? So as I said, we want to avoid any recompilation overhead. And in this setting, not only are we beating the latency on the communication pipeline, but we are also leveraging our core technology of the OPX, the hybrid processing unit, to fine-tune in real time the pulse parameters. This means that the 3 parameters we selected, namely the amplitude of a flux pulse for a CZ gate applied on a flux-tunable transmon qubit architecture, as well as 2 other phases, will be modulated in real time without triggering any recompilation of waveform whatsoever. And this is really at the core of our technology, because we are embedding the best of what we can do at the lower level with our OPX to some extremely low latency framework with the DGX. Let's see how it works in practice. So, first of all, let me try to give you a glimpse of what the core program is about. How do we build a program which is connecting us to the DGX Quantum? Mainly, how do we make the connection with the Grace Hopper? So, in this particular case, we created a very flexible framework in which you can write in a few lines of code the pipeline to send and stream back actions and rewards for between the 2 entities. So in this particular command over here, you see that at the beginning of a training step, we are waiting for a new action. Once we receive this action, namely the set of 3 parameters, we are ready to proceed. We can now execute our quantum circuit. So this is exactly what we'll be doing right next. We are now doing a real-time full loop over the number of shots. Remember, the OPX 1000 enables you to trigger all kinds of classical processing, but also real-time control of flow. So you can write everything that you would think about, such as for loops, if-else statements, while loops, and so many others that you could think about. The beginning of the program consists in making sure that we have the actual circuit to prepare the bell state that you can see on the right. Because our basis gates are based on a CZ architecture, and we want to prepare a bell state based on a C0, we are applying some single qubit gates to make sure that we end to the right target state. And next, we make sure that we can process correctly all the parameters that make our agent ready to apply those things on a quantum computer. In this particular case, we have our framework QAM, which enables you to very simplistically call the quantum gate CZ, but modulate its pulse output with real-time adjustable parameters. So this is exactly what you see in this command in this case. Once we executed this modified customized CZ, we are ready to do the measurement. So remember that now we are interested in measuring 3 different types of the expectation values. In a flux-tunable transmon qubit architecture, we have only one native measurement available, the one in the computational basis. In order to measure XX or YY expectation values, we will need to rotate the basis prior to measurement. Usually, this would involve slightly modifying the quantum circuit by applying some rotation gates such as Hadamard gate and phase gates. Of course, we want to avoid having to load 3 different circuits for the same task. So we're going to, again, leverage the real-time control flow structure of our OPX to make sure that we can compute those expectation values without any overhead. So this is exactly what we're doing here. Depending on the axis that we chose, we can apply dynamically those pulses to make sure we're measuring the right basis. Once we apply those pulses, we are ready to do the readouts, do real-time state discrimination, and based on the counts, the measurement counts that we're collecting, we can also compute readout error mitigation. So here we have pre-calibrated a confusion matrix, which is going to enable us to push even further the computation and making sure that we suppress readout errors. Finally, we are now ready to do additional classical processing to combine all the information we collected for those counts and build this fidelity estimator whose formula is on the right. Once we collected this estimator, we are ready to send back the reward. And this is exactly what this function is about. This send to DGX command basically sends from the OPX, again, with a almost 2 microsecond latency, 4 microsecond latency as round trip, so only one trip will be 2 microseconds, back to the Grace Hopper chip. And in this particular case, we're making sure that the packet is as small as possible to make sure that we are super efficient and lowering all compilation overhead. Once the agent will receive this reward, the neural network will be automatically updated with new parameters, inducing a new strategy, a new policy to try different action parameters. Now, in reinforcement learning, the beauty of it all is that we want to test out and deal with the exploration-exploitation trade-off. What does it mean? With reinforcement learning, as a model-free method, we want to be able to get an overview of what the parameter space is about. As I said before, the compilation overhead could be quite huge in principle if we're not careful and want to explore too many parameters. But in our scenario, this trade-off comes for free. It's exactly the same cost. You can either explore different actions or compute many shots for one action for full benchmarking. This is exactly the same execution budget. So what has been shown in the literature is that it's actually advantageous to aim for exploration, especially when we are in this case where we don't have any idea of where to start. We don't know what our parameters are. So let's run the demo and see how fast it really takes. Here we go. So we're going to load the program. So what we're doing now is executing this full program we are on a DGX Quantum architecture located in the Israeli Quantum Computing Center in Tel Aviv. We'll wait a few seconds and we should see appearing, yes, here it is. We see appearing a learning curve. As you can see, it's pretty impressive to see it live, right? So in a matter of a few seconds, what we are seeing here is the agent iteratively updating its strategy to ensure that the parameters that it chooses are effectively increasing the reward. And namely, the reward is the fidelity in this case. So in a matter of a few seconds, we identified a scenario where we have a fully functional CZ gate ready to be applied in a quantum computing setting. And the great news about this is that this framework is fully extensible. You can apply many things on top of this standard gate calibration. For example, what if you wanted to make your gate calibration context dependent? For example, the parameters would depend on the circuit in which you are trying to execute this. This is typically what we are doing at QM, pushing the research to new cutting edge, leveraging all that we know about the lower level OPX 1000 structure. With that said, I hope I convinced you that DGX Quantum is definitely the future of quantum computing. With this bring up in a matter of a few seconds, we anticipate that fault-tolerant workflows will be closer than ever. Thank you very much.